Today, we'll be looking at a paper called Unpaired Image-to-Image Translation using Cycle-Consistent Adversarial Networks, or CycleGAN. This CycleGAN paper tackles the problem of image-to-image translation, which is a problem of translating images from domain A to domain B, such as converting images of zebras to horses, or summer to winter, or mono to photos, and etc. However, this paper especially tackles the problem of unpaired image-to-image translation, which is quite difficult because since there is no target for converting zebras to horses or converting summer to winter, there is really no target for the model to learn from. However, it is still an important problem because unpaired settings are more common in real-world situations because let's say you want to make a model that translates from zebras to horses. How are we going to even obtain a paired dataset? You have to obtain a dataset where the horses and zebras are at the exactly same pose, exact same shape, in the exact same location, and you need like thousands of these photos. It is near impossible, and that's the reason why this unpaired image-to-image translation task is really important. Now let's look into detail how the paper achieved this. So this is the basic problem formulation where you have a image from domain X and domain Y, and these are unpaired. So this is achieved by a constraint this paper suggests called cycle consistency loss. So cycle consistency loss starts from a intuition where when you translate an image to its target domain and you translate it back to its original domain, then the resulting image should be similar to its original input. Now let's come up with an example. For example, let's say that you want to convert an image of a zebra into an image of a horse. And what you expect from the translation is that you want everything in the input image to be preserved, like the poses of the animal or the shape or the background. You want all of these to be preserved except the stripes on the surface of the zebra, and you want it to be replaced with a brownier or whiter color. So what's kind of intuitive is that let's say that you have a model G that does this task of translating from zebra to horse, and let's say that you have another model that translates from horses to zebras. When you apply the model that translates from horses to zebras back on the translated image here, then the image translated back would be similar to its original input. So this basically means that when you translate an image from domain X into domain Y, and then translate it back into its original domain, then the resulting image should be similar to its input. So this is a quite intuitive formulation of the cycle consistency loss, and the model achieves this by the same way, G and F, where an image from domain X enters the generator G, and this enters the generator F, which translates from Y to X, and you want this resulting image to be similar to the input X. So this is called the forward cycle consistency loss, where in the example for zebras to horses, you want the conversion from zebra to horse back to zebra to be similar to its input. And the next case is the backward cycle consistency, where putting Y as the input to F and putting that to the input to G would be similar to the input Y. And this is similar to converting horse to zebra, and when you convert that back to horses, it should be similar to its input. So that was both the forward cycle consistency and the backward cycle consistency. So it's in my opinion, a pretty straightforward loss function. However, these two loss functions aren't really all we need. So we have the cycle consistency loss, but the easiest way to minimize this loss is for G and F to learn an identity mapping. So that way, when we put X into the G, it will produce X, and when you put that into F, it'll just produce X and look similar to the X original. So even though cycle consistency minimizes the distance between the input and the translated back version in both directions from x to y and y to x, it doesn't really ensure that the translated images look like they're from either domain y or domain x. So because of that, the network doesn't really care about whether the images generated from G really looks like it's from domain Y, or images generated from F really looks like it's from domain X. It just wants to minimize this cycle consistency in the easiest way possible. So we need to regularize so that both each G and F generates images from domain Y and domain X. And this is done using GAN, or Generative Adversarial Network. So GANs, or Generative Adversarial Networks, is a way of generative modeling that generates images in an unsupervised manner. So GANs typically have two networks, where the first G, the generator, and this D, the discriminator. The G receives a random noise vector Z and produces a output image, and what D does is it receives an image and predicts whether that image is actually from the real image that we want to learn from, or it is a fake image that is generated from the generator G. And G's goal is to generate the output so that the D incorrectly classifies it into thinking that this is a real image, and D's goal is to translate the input image well between real and fake. So since G and D has opposing objectives, when we train these two simultaneously together by this GAN loss function, it's a minimax game where you want to minimize this term for the generator G and maximize it for the discriminator D. So GANs are typically the method for generating high-dimensional images in an unsupervised manner, and it is able to generate pretty high resolution and high-quality images well. So this GAN is typically a unsupervised, or it isn't conditioned on anything. It just learns from the data. However, we can still condition this GAN on some kind of an input. So that is called a conditional GAN, where instead of simply generating images from a random noise vector Z, it also receives some kind of a condition together, which might be either the label of the image we want to generate, or a input image in our case from the input domain X. So that's the conditional GAN, and the CycleGAN also adopts this conditional GAN as a part of its component to make sure that both each G and F generates images that are that looks like it's from domain Y and looks like it's from domain X. And since there are two generators, both G and F, there needs to be two adversarial losses as well. So this first loss is the GAN loss for generator G, to make sure that G generates images that are looking in domain Y. And we also have this discriminator dy, which serves the purpose of classifying whether the image produced by G looks real or looks fake. And the same goes with F, where it also has a GAN loss and a discriminator dx, where it discriminates whether the output produced from F really looks like a real image or a fake image. So this GAN loss for G and dy and the GAN loss for F and dx are simultaneously used in the final loss function. And the cycle consistency loss function, as mentioned before, should minimize the result between the input and the translated back output. So it simply minimizes that by minimizing the L1 loss distance, like this. So it minimizes the pixel space difference between X and the translated back output and Y and the translated back output. So the full objective becomes minimizing the GAN loss for G and dy f and dx, and cycle consistency loss for both generators, g and f, which is multiplied by the coefficient lambda, which determines how much importance we want to put in the cycle consistency loss. So having a low value of this lambda will make sure that make the network less care about the cycle consistency loss, and this really depends on the domain of the problem. And since GANs are a min-max problem, we want to minimize this for the generators and maximize it for the discriminators. So when looking at the components again, the first component makes sure that the outputs from G are realistic. And looks like it's from domain Y. And the second component makes sure the F generates realistic images that looks like it came from domain X. And only having these two loss functions are also not a really good choice, because then in the case of converting zebras to horses, it would simply generate a random looking horse. It doesn't really care about the input it receives, no matter what input it receives. It only has to generate a single realistic looking horse, because that's all the generators and the discriminators care about. So that's the reason why we need the cycle consistency loss to ensure the semantics are preserved between the input and the output. So this preserves semantic. And for all experiments, the lambda, the coefficient here is set as 10. And the network is using the residual architecture, and is trained either on 128 by 128 or 256 by 256 images. And what's really important to note here is the discriminator architecture, and it uses a 70 by 70 patch GAN discriminator. This architecture originally came from the Pix-to-Pix paper, and what does it mean by 70 by 70 is that when it receives a image, the receptive field of the entire discriminator network is 70 by 70. So what it means by that is the output, when this discriminator produces a output, a single pixel of that output is influenced by 70 by 70 region of the input, because of how convolutions only work at a local level. And as it gets stacked up, the receptive field increases. So this is a pretty shallow discriminator, and the reason why they chose this design is because since it only looks at 70 by 70 patch of the image, it cares more about the local information. So in cases of translating from zebras to horses, we don't really need the entire information of the image. We only need to look at the patch and convert it, which is more easier. So this 70 by 70 patch GAN makes sure that it translates the image at a more texture-based level. But the problem with this 70 by 70 patch GAN is that it can't really change the image a lot. It can't change the image at a global level because the receptive field is very limited. For example, let's say that you want to translate from cats to, let's say, dogs. And when looking at only the 70 by 70 patch level, it is often very difficult to really identify whether that patch is from a dog or a cat. So in that case, it is important to have a larger receptive field. So I think this also depends on the task, but the paper here used only 70 by 70. And for the GAN loss, they actually didn't use the GAN loss formulation above here. This is the original GAN loss from the original GAN paper by Ian Goodfellow. This is a GAN loss function called non-saturating loss, where it has log here. But the paper instead uses a variant of this GAN loss called LSGAN, or least squared GAN, where it uses a least squared loss. And this paper claims that using the LSGAN loss results in a much more stabler training. So this was the overall explanation for the CycleGAN framework, and what is really interesting to me was the later experiments on the CycleGAN framework. So they did some evaluations like the Amazon Mechanical Turk these are actually people classifying whether the output looks real or fake. And the CycleGAN result outperformed all the other competitors. And they also trained the CycleGAN in the task of converting a semantic map like this. This is a cityscapes dataset where we have a semantic map and a corresponding real image. So semantic to image, and since you have a corresponding image in this case, we can actually evaluate it more quantitatively. So what this did is, when converting cityscapes label to photo, we used a off-the-shelf semantic segmentation model to convert the translated photo back into label space, and comparing the per pixel accuracy per class accuracy and the class IOU. So you can see that the pix-to-pix, by the way, is a paired image-to-image translation method. So pix-to-pix, of course, outperforms all the other unpaired methods, but still among the paired methods, among the unpaired methods, CycleGAN is superior to all the other examples. And of course, in the photos to labels, and of course, when converting photos to cityscapes labels, the per pixel accuracy or class accuracy IOU, CycleGAN outperformed all the previous methods. And the ablation study was also really interesting. In this part, they analyzed the component of the individual loss functions. So to recap, there was the GAN loss function for G, the GAN loss function for F, and the backwards cycle consistency loss and forward cycle consistency loss. Let's just treat this as a single GAN loss, by the way. So when we have an input, when using cycle consistency alone, you can see that the outputs aren't really realistic. They look completely different from the actual target domain. And that's the reason. And the reason for this is because we never explicitly regularize the outputs to look like it's from the target domain. And we only want the network to make sure that it can translate this back to the input image. So that's the reason why this learned a unrealistic output. And this time we used the GANs alone. And at first glance, it might seem like a pretty good result. But the problem is that, you see, no matter what input it received here, it produced an identical semantic mapping. So this is a problem known as mode collapse, where no matter what input it receives, it just outputs a single output. And that's because since this is only optimized on GAN, its only objective is to make it sure that the output looks realistic, and that's all it does. And next, they tested on GAN plus only the forward consistency loss and GAN plus the backward consistency loss, and it still has some problems with mode collapse. But when we use all these loss terms together in a full CycleGAN framework, the outputs are the best. They also trained this on other tasks like labels to facades or edges to shoes, and shows that it works pretty well. And one additional problem they found in the task of converting paintings to photos was that the CycleGAN with these loss terms aren't really enough in terms. CycleGAN with these loss terms aren't really enough in certain cases. For example, this is a task of converting paintings to photos. And you can see that even though the input painting is a yellow tinted image, the CycleGAN produces a blue tinted image. So let's look at why this happens in terms of GAN loss, in terms of CycleGAN loss. So first, you have a GAN loss and a cycle consistency loss. And let's check if the results are realistic. They do look realistic, so the GAN loss isn't a problem, but the cycle consistency loss might be a problem. So you have this generator G that translates from yellow tinted image to a blue tinted image. But what the F does is it undoes the translation that G did in terms of color transformation. So if G translated from yellow to blue, F translates from blue to yellow. So it undoes the unwanted transformation in the G network. So even though the cycle consistency is satisfied, it still produces a output with different color. And this isn't what we really want in this painting to photo problem. We want the output color scheme to be similar to its input. So that's the place where this identity function comes in. So what this identity function comes in is, you have this G and F that each translates from X to Y and Y to X. But what the identity function does is, instead of putting X in the input of the G, it puts Y as the input of the G, and then X to the input of the F, and then minimize the output to Y, and minimize the output to X. So basically, this is telling that when the generator receives a input from the target domain, then it needs to be an identity mapping. So let's see what happens when we also try to minimize the identity loss. So this G now receives a photo image, let's say a pink tinted photorealistic image, and the G now when receiving this pink tinted image, originally will convert this into a blue tinted image. But now, because of the identity loss, it also has to produce a pink tinted image with the same color. So by minimizing the identity loss, we can implicitly ensure that the input and the output will have a similar color. So this identity loss was only used in the problem of converting paintings to photos, because this is the task where maintaining the color is really important. So this, in my opinion, was a pretty interesting addition to the network, to the framework. And of course, CycleGAN has some limitations. So these are the typical failure cases of the CycleGAN approach, like the task of dog to cat transformation here. And this is where the problem I mentioned previously exactly comes in, because the 70 by 70 receptive field isn't really enough to classify whether a certain region looks like a cat or a dog. So in this case, we might change the architecture of the CycleGAN to have a higher receptive field to capture the entire image at one go. So to increase the receptive field so that the discriminator can see the image at a more bigger level. So in this case, we can make the discriminator more deeper so that the discriminator sees the input at a much global scale. And similar cases like here, apples to orange, since the network only sees a patch of the image, it really can't learn to transform the image at a global scale. So you can see that the translated orange still has its peak on it. And another problem was when converting horses to zebras. When there is a person existing in the image, it also converts the image. It also converts the person into a zebra. So this is a unwanted transformation, and this might not be a problem of the CycleGAN architecture and this might just be a bias in the data, because in the dataset that's trained for this model, horse to zebra, they used the wild horses images in the ImageNet dataset, which doesn't really contain images of people riding on the back of the horses. So since the network didn't really see a person during the training, it might have not generalized and thought this person as part of the body of the horse or the zebra. So overall, this was the explanation for the CycleGAN paper, and this is a pretty old work. There has been many advancements in unpaired image-to-image translation that tackles a lot of the problems mentioned here, such as unit, M-unit, F-unit, and many other papers. But CycleGAN is still important because most of the unpaired image-to-image translation methods, even used nowadays, still use the cycle consistency loss. So I think this was a really interesting paper to read and review. So if you liked the video, please leave a like. And if you have any comments or suggestions, please leave them in the comment section below. Thank you.